PLC Edge Analytics is a heavy-duty, stateful background worker, processing physical asset states concurrently on highly constrained edge hardware environments. Building software to survive this environment requires strict C# engineering discipline. The entire codebase adheres rigidly to clean architecture and domain-driven design principles. This means the central domain layer operates in complete isolation. It contains the business logic and physics contracts with absolutely zero database or external framework dependencies. To enforce predictability across the application, the codebase utilizes functional programming paradigms provided by the language extend library. In an operational technology environment, standard try-catch blocks and implicit null references leave too much room for silent failures. An unhandled exception can mean missing a critical machine fault. Instead, absence and failure are typed explicitly into the method signatures. Using constructs like option and either, the compiler forces developers to handle every specific error state before the code will even compile. We also intentionally removed mediatar. In its place, a custom command and query messaging scheme enforces tighter generic constraints and guarantees thread-safe runtime services. These structural constraints prevent the system from ever presenting a false machine state to an operator. The software survives volatile edge hardware because the architecture demands absolute determinism. Telemetry arrives through a universal ingestion engine. Because velocities vary, storage splits into two engines. SQL Server 2025 is the relational hub, maintaining core states, ML artifacts, and vector embeddings. TimescaleDB manages hot time series data, absorbing the intense write load of continuous telemetry. When live data streams from a physical programmable logic controller at 1 Hz, Debezium change data capture mirrors those updates. It routes the stream through RabbitMQ directly into the TimescaleDB hypertable with sub-second latency. To coordinate these two engines, a specialized abstraction layer called the hybrid historian reader sits on top of both databases. This reader shields the downstream application. The analytics engine requests a window of data, and the reader automatically resolves whether to pull hot telemetry from Timescale or historical replays from SQL Server. For high-velocity, non-relational tasks, Redis secures distributed training locks and maintains Blazor signalar state across concurrent background operations. By separating the heavy relational state from the intense time series writes, the system avoids database deadlocks. The analytical pipeline continues processing without dropping telemetry during traffic spikes. The continuous inference loop service drives the application. Every 10 seconds, it pushes a 2-minute rolling window of telemetry through a 21-step pipeline. Raw signals undergo advanced digital signal processing, calculating rotational polar features to extract spectral targets from the background noise. These extracted features pass to the MLNet orchestrator facade, which coordinates a multi-strategy machine learning fusion. The pipeline simultaneously evaluates 15-dimensional feature vectors using singular spectrum analysis and randomized principal component analysis to identify anomalous patterns. Running these heavy inference models concurrently on physically constrained edge devices demands an absolute strict level of hardware pragmatism. We utilize the Intel OpenVINO execution provider to offload mathematical processing directly to the device's integrated UHD 770 graphics processing unit. If the hardware lacks a compatible GPU, the execution chain guarantees a silent, immediate fallback to the primary CPU. Evaluating the data against multiple concurrent machine learning strategies within strict time limits ensures that a single drifting model cannot trigger a false plant alarm. Detecting a mathematical anomaly is only the first step. To maintain operator trust, the system must aggressively suppress raw statistical deviations before they reach the plant floor. Candidate anomalies face a strict 4-gate validation chain, crossing a statistical score threshold, maintaining 90% ensemble confidence, persisting temporally, and surviving strict physics bounds. Verified anomalies then enter the graph intelligence layer, mapped entirely in memory using QuickGraph and MathNet numerics. We explicitly rejected network-dependent graph databases like Neo4j. At the edge, database round trips introduce latency, so we rely entirely on pure in-memory matrix mathematics. The system calculates the Fiedler eigenvalue of the asset graph to evaluate overall structural stability. By continuously running algebraic connectivity checks, the runtime detects when multiple interconnected assets begin degrading simultaneously, indicating systemic factory fragmentation. This topological analysis identifies cascade risks across connected machinery well before any individual sensor tag breaches its hard limit. The combination of strict physics gates and topological matrix math ensures operators respond to verified mechanical failures rather than isolated sensor noise. Deploying generative AI into industrial control systems carries immense risk. A hallucinated set point or a fabricated diagnostic instruction could lead to catastrophic physical consequences. We mitigate risk using the Ops Narrator pipeline, a strict sequence of triage, diagnostic, RAG context, and narrator agents chained via the Microsoft AI chat client. Routing is hard-coded in C#, stripping the language model of any autonomous decision-making over the execution path. Instead, an internal plugin exposes deterministic Bayesian fault decomposition, executed in pure C# code. The actual generative component relies on a locally hosted Phi-3 mini model running entirely on the CPU. The Phi-3 model never calculates probabilities. Its sole function is to synthesize the deterministic mathematical facts handed to it by the code execution context. Before any narrative reaches the operator, it must pass the final Phi-3 output guardrail. This guardrail executes fast, zero-latency string operations, evaluating the final text against rule-based checks to instantly trap and discard hallucination markers or fabricated data patterns. Generative AI becomes safe at the edge only when the language model is completely subordinated to a deterministic, mathematically bound execution engine. To ensure industrial alerts are never lost to network partitions, we utilize the transactional outbox pattern as our final layer of reliability. Every verified anomaly and its operational message are committed safely to the local SQL database first, before being dispatched downstream to RabbitMQ. When hardware environments are volatile or external dependencies fail, the system falls back on safe degradation patterns. If a target PLC lacks explicit policy approval, the write-back pipeline safely degrades to a null PLC writer stub, logging the attempt without modifying physical machinery. Similarly, if the local language model becomes unavailable due to memory constraints, the pipeline degrades gracefully. It returns strict, deterministic rule text definitions rather than failing the inference loop. By enforcing guaranteed transactional messaging and explicit degradation paths, we ensure the plant floor never executes physical actions based on ghost data or partial network failures. The Blazor-based operator interface functions as a transparent explainability workspace, exposing the system's pure mathematical truth. It directly exposes the Wrecking Ball Evaluator, an 8-dimension scoring matrix analyzing physics, context, and historical patterns, allowing a human operator to audit exactly why an alert fired. The interface also renders green SHA-256 provenance seals. These hashes mathematically verify the origin of every cited calculation back to its exact engineering source. The entire runtime is monitored through an observability stack combining OpenTelemetry, Prometheus, and Grafana. By tracking precise internal metrics down to the execution duration of individual local language model narratives, we maintain absolute transparency over the system's hardware footprint on the edge device. True industrial intelligence cannot be a thin API wrapper glued onto a dashboard. It requires a resilient, mathematically rigorous runtime built specifically for the edge.